perform similarity transformations. Hopefully by the end of this class you'll be able to perform some dilations and kind of talk about them intelligently. We've already kind of studied a little bit about what dilations are. There's just a transformation that either stretches or shrinks a figure. These are probably terms that you've heard maybe in middle school. In a dilation, a figure is either enlarged or it's reduced, and it's always going to be in respect to a fixed point. Generally speaking, in this class, we'll talk about that being the origin, 0, 0, if it's on some sort of Cartesian coordinate plane. Other times, if there's just two single pictures and there's no x or y, then we just have to talk specifically about what the center of dilation is. Whenever you mention a dilation, there always needs to be a dilation. You need to mention dilation, you need to mention the center of dilation, and also the scale factor. Again, the scale factor is the ratio from basically the image on top, the image to the pre-image on the bottom. So where you end over where you start is kind of the way that I think about this. So from the image to the pre-image is how this ratio will work. At the bottom, we're actually talking about some notation. So if our scale factor was something like 3/2, then what we can do is we can actually write this in notation. X comma y is where we start, and we'll go through and they'll map onto 3/2 x as well as 3/2 y. Remember that a dilation is going to affect both the x and y evenly. If you ever see one that only has one part here, like 3/2 x, but something else y, that's not really a dilation. And always some things to note is that if the k is greater than 1, such as 3/2, it's going to be an enlargement, it's going to be getting bigger, so from, say, the blue to the red. If it's between 0 and 1, like if this was 2/3, that might be from like the red to the blue. It's called a reduction, which makes sense to us. These are kind of words that we hear every so often, like a reduction in salary or enlargement in salary. We understand what those words mean. If there's ever like a negative involved, the negative actually does not point to a dilation. It talks about a reflection of some kind or some other type of transformation. So the negative, these numbers always have to be greater than 0 when we talk about them to just be a dilation. Take a second and we'll just use this idea that if k is our scale factor, we're just going to increase this. The way I think about this, and this will be kind of independent of wherever your center is. Right now my center is 0, 0. My slope from the center into A is I go up 1 and over 1. Well, with a k of 2, that means I'm just going to double that, so I will go up 2 over 2, and this will be my new A prime. For B, I go over 2 and down 1. I'll double that. I'll go over 4 and down 2. This point right here will be my new B. For C, I just go over 2. I'll double that. I'm now going over 4. That's my C prime, just like that. The same concept works with a reduction of 1/4. This is up 4 from our origin, so I'll go just up 1, I guess. That's A prime. This is actually over 4 and down 4, so that's just going to be right here for B prime. This is over 4 and down 4, so this is going to be C prime right here. You draw your little picture, and this is going to be a reduction of our original figure. Determine whether the dilation from figure A to figure B is a reduction or an enlargement, then find the values of the variables. Remember that you're going from A to B. So you start at A, you go to B. A lot of students mix this up just on accident. They just look always from the left to the right or something like that. This case, you're going from A to B, so are you getting bigger or smaller? You're getting smaller, so that would be a reduction. Then we look at this. Sometimes you can just use your brain for this. You don't have to necessarily set up a ratio. If we go from 6 to 2, we're basically dividing each of these numbers by 3. So 3 divided by 3 would give me x equals 1. 6 divided by 3 would give me y equals 2. And 3 divided by 3 again gives me z equal 1. That's not very tough. If you needed to, you could have set up some sort of ratio like this. 6 over 2 equals 3 over x, and cross multiply and solve. And for harder ones, maybe that's a better idea. For number 6, again, we're going from A to B. So in this case, this is going to be an enlargement. When we look at our variables, we find two that do match, corresponding sides that do match. So that's from 7 to 14. So it looks like we're doubling. So that means n is going to equal 20. It was 10, now it's 20. This is 8. This is now going to be 16. Use the given point coordinates to determine whether the triangle DEF is a dilation of triangle ABC. A lot of students mix this up just simply because they're not sure where these triangles go, where these points go. We're looking at the end over the start. So reading this is sometimes difficult because you don't know where you end and where you start. Determine whether this triangle is a dilation of this. It sounds to me like we start with ABC. We're trying to determine if DEF is a dilation of it. So I would say this is triangle ABC, and on top is going to be triangle DEF. Sometimes determining that, setting up some sort of ratio like this, does help. Then all we're going to do is we're going to compare each of these numbers. So for A, we're going to compare A's first coordinate, the x coordinate, to D's first coordinate. We'll have 36 over 42. That simplifies simply down to 6/7. Hopefully that's going to be equal to the y coordinate divided by the y coordinate. So we'll say 24 divided by 28, and we'll set that equal to 30 over 35. I'm just pulling these numbers from here and here. I'll keep going with this. We'll have 12 over 14, another 12 over 14, and then finally a 16 over 21. Now, ideally, all of these are going to simplify to the exact same number. That number is going to be our ratio or our scale factor. And I'm running this end over start, so that should be significant. So this is, that would equal 6/7. That's good. That equals 6/7 because they're divisible by 5. This would equal 6/7 because it's divisible by 2. Same thing here, divisible by 2. And then this guy, I don't know. I can't simplify that any. So because of that, these triangles are not similar. Okay, so be careful with that. Those are not similar. You do not have a scale factor. If this would have been something different, that would have given us this ratio of 6/7, we would have definitely had it. Next, we'll look at the second one. We'll set it up in the same way. Again, it is triangle DEF is where we end. Triangle ABC is where we start, so we'll just set things up this way, and then we'll just start dividing points. So we'll say negative 72 over negative 54. These are going to probably be harder fractions, but not really a big deal. 144 over 108. Then we'll say 60 over 45. That's just getting point E and point B, which are the corresponding angles, E and B. Next, we'll say 48 over 36. Then we'll say negative 96 over negative 27, and negative 24 over negative 18. You have to be careful with this. I wrote this one incorrectly several times because when I'm looking at this, I say negative 96 and I see negative 72. And I'm supposed to be looking past that. I'm supposed to be looking at the negative 27. So just kind of watch that as you're putting points in here. Just make sure that you're getting the right ones with the right ones. When I divide this, this would be 4/3. This is 4/3. This guy's 4/3. This guy's 4/3. The last one's really easy to do. That one's 4/3. But this guy here, not 4/3. If you pretend for a second that it would be 4/3, I just want to show you what it would look like. You'd say, yes, this is a scale. This is a dilation. If this did work out, obviously this is the one that throws everything off. It is a dilation. It would have a scale factor of 4/3. And then if you have to write this, the center would be the origin. I think it's always important to include this, the center of the origin. I didn't spell origin right. There's more letters in there. If you were to try to write this using this notation, again you just write 4/3 x for the image and 4/3 y for the image, and that would really help us out. So yes, it is a dilation. It has a scale factor 4/3 with the center of the origin. And this would be the way that you'd write it out using the notation. Next, draw the dilation of the polygon that has the given vertices using the given scale factor. So when I look at this, the way that I was taught to write this out is to just write your points. So A, B, oh, this is really bad handwriting, C, here's D, and this is going to map onto something. So there's these little arrows that say you're going to map onto some new points. And that'd be A prime, B prime, C prime, and D prime. So these are going to be some new points. And all we have to do then is we take each of these individual points, the x and the y, and we're going to multiply it by 5/3. So 5/3 of 3 would give me 5. 0 times 5/3 is 0. 6 times 5/3, that's 6 times 5 is 30, divided by 3 is 10. Negative 3 would give me negative 5. 3 would give me 5. Negative 6 would give me negative 10. 0 gives me a 0. And negative 3 times 5 is negative 15, divided by 3 is negative 5. And then we would go through and I would plot these points. It's kind of weird because it's on a scale of 2s. So this would be 5, 0. This would be A prime. B prime is over 10, so 2, 4, 6, 8, 10, and then down 5, 2, 4, 5. This is B prime. D prime is right over here, D prime, and C prime is going to be down here, over 5, and then down 10, 2, 4, 6, 8, 10. This is going to be C prime. I should probably connect these. Oh, this is not looking pretty. Looks something like that. Okay. Same concept is going to go for the second one. It does say to draw it, so you need to make sure to draw it. I'll just show you. You're going to just divide everything by 6, so that would give you 1, 4. B prime would give you 4, 5. C prime would give you 3, 1. And D prime would give you 1, 0. You quickly plot this. 1, 4, 1, 2, 3, 4. This is A prime. It's always a good idea to label these. B is 4, 5, 1, 2, 3, 4, 1, 2, 3, 4, 5. This is B prime. You guys know how to plot things, so this shouldn't be a big deal. 1, 2, 3 of 1. This is C prime. And D prime is just over 1 up 0. So this right here is D prime. Connect your lines. Look at how good you are. You're set. Okay. Last thing, says the polygon shown is the image of the polygon. So this is after some sort of dilation has happened. Okay. Find the coordinates of the vertices of the original of the pre-image. Here's how this works. If this is what happened, to undo it, we basically use the reciprocal. So we're just going to multiply each of these coordinates by 3. So our pre-image is what I'm going to label here, our pre-image. So I would have a pre-image M. M is over 0, up 3, so it's going to become over 0. 3 times 3 is 9, so pre-image M would be this. N is over 2. 2 times 3 is going to be 6. It's up 1, 2, 3, 4. 4 times 3 is 12. L is over 1, 2, 3, 4. 4 times this would be 12, and this would give me 0. These are the pre-image coordinates that if these went through a dilation of 1/3, they would give you this. But since we're going backwards, we're multiplying by the reciprocal. I don't think this is particularly difficult when we talk about this, especially with the idea that we know how dilations work. I don't think it's that tough, especially when we have really nice numbers to reciprocate. So could it be more challenging when you have weird numbers and you get some weird fractions? I think it could be. This is just turned to 5/3, 7/3. This is 1. This is 1/3. This is 3, and this is 1. So sometimes you get fractions. Not a huge deal. You just know how to handle this. Again, we're talking about just performing these. The goal was that you would be able to draw dilations, talk about them intelligently, whether they're enlargements or inductions, reductions, be able to talk about the scale factor properly just to make sure that it's end over start.